All right, so our goal today is to start to talk about electric potential. But before we get to electric potential, we need to talk a little bit more about electrical potential energy and work. So when we're looking at energy, we start essentially with force because energy is related to the work being done. So if I wanted to find the work being done on a particle due to some particular force as it moves between two locations, then I would set up this integral here where dl would be the path length. Okay, so it would be the path length that was taken. So if the force is conservative, then the work is equal to negative the change in potential energy. So this is something that we did last semester, so pulling that back in. So the work from A to B would be equal to negative the change in potential energy. If the first force is conservative, then the total energy would remain constant. So if I define my system to be the particle, then the energy of that particle should be constant. And then you can write a conservation of energy statement such as this one. Now, let's talk specifically about an electric field here. So if we have this electric field pointing downwards, and point A is a point on, like, say, that top plate, and B is a point on a bottom plate, as Q moves through some sort of displacement from A to B, then there's going to go through some, basically on the separation distance of those plates. So the force that we would sub into the work equation would be Q0 times E. Okay, so that's just the force on a test charge due to an electric field. This is a uniform electric field, so that electric field in this case is constant. The direction of the force will be dependent on the sign of the charge. So Q0 does need to include its charge. So in this case, our test charge can either be positive or negative, and this equation would handle that. So the work being done is independent of the path being taken. So if he goes straight from A to B, then that would give a certain amount of work. But I could also go from A to B like this, or I could go like this. And in either case, it doesn't matter. As long as I go from A to B, the amount of work is going to be the same. And that's because our electric force is a conservative force. So if we wanted to then find the work, so we could find the energy, you would then sub in. So they've changed their variable here from DL to DS. I'm not sure why they did that, but there's lots of different ways I've seen this represented. S is sometimes the path, L is sometimes the path length. But the idea with this dot product is we're not just taking the whole path length, we're just taking the portion that's parallel. So if you sub in that Q0E, then we get the integral from A to B of Q0E dot ds. And we want only the portion of the path. So even if I do something crazy like this, only the portions of that path length that are actually parallel to my electric field E matter. So I don't actually therefore need the dot product if I consider only the portion that's parallel. So if we do take that dot product, then essentially that's going to equal E dy. So if I take, what this is saying, just to kind of get a visual, is if I take some little tiny section of path length here, and that little path length is ds, then what I do is I take define dy to be just the portion of ds that is parallel to E. And then what we're going to do is with this integral is we're going to add up all of those little possible dy's from each of the little possible sections and add that up for the entire path from A to B. So if you sub that in, then we get an integral from a to b of q0 e dy, which is much easier to handle than having a dot product. Anything we can do to get a dot product out of our integral is good. So the electric field's uniform in this case, not in all cases. So we're going to see another case where the electric field is not uniform. But since the electric field is uniform, it is constant. So therefore, and the charge can be pulled out in front. So we get q0e times the integral of dy. And then that is something we can integrate. So if we integrate that, you're going to get y from a to b. So if you plug in y at b minus y at a. And then, we're defining that as d. So basically, yb to ya, because we're going the entire distance of this plate, is d. We could just move through part of the distance. So we could have a y value that is different than the whole separation distance of the plate. But in this case, we're assuming it's going from a to b. So therefore, the work is going to be q0 ed. And when we look at potential energy is going to be negative delta U. So if we want to solve for delta U, it's going to be negative the work from A to B. So we're going to get that the work is equal to negative Q0 E times D. So this is a really important result. And this would be a good thing just to remember because they like to use parallel plates. So having that answer without having to do the full derivation is always super handy. Now notice that it is negative Q0 E times D. So this is going to be kind of like the potential energy that we saw with gravitational potential energy, except for with a little twist, because Q0, unlike mass, can be positive or negative. So gravitational potential energy was always negative because everything else in the equation was positive, or at least was a scalar value. In this, Q0 can be either positive or negative, which means our potential energy can be either positive or negative. So we get our final result, delta U is equal to negative Q0 E times D. So if we take a look what's going on here, we have, in order to have this electric field, that top plate had to have been positively charged, and that bottom plate would have had to have been negatively charged. So basically, if we were to put a positive test charge, then that positive test charge, placing it, if you think about it, is going to be very strongly repelled and is going to want to easily come back down here towards the negative plate. So if you think about it, that's kind of like an object falling down a hill. The tendency of that particle is to move in the direction of the electric field. Now, if we were to have placed a negative charge, that negative charge is already where its attractive forces are the strongest because it's being repelled by the bottom plate and attracted by the top plate. So if I want to move that negative charge from A to B, I essentially have to force it to do that. I have to do work on the object. So there's a big difference between the behavior of a positive charge and the behavior of a negative charge when we move with the electric field. So with a positive charge, when the particle moves in the same direction as the electric field, that positive charge is losing potential because the positive charge being at the negative plate is the lowest potential. It's like a ball having rolled down to the bottom of the hill. It's not going to roll back up to the top of the hill on its own. You're going to have to do work to move it up there. Whereas the negative charge is opposite. Essentially, the bottom of that potential hill is going to be at the positive plate, and you're going to have to do work to get it back up to the negative plate. And remember, when you have to add work into your system, that is always going to be a gain in potential energy. When work is done on the system, by the system, then you are going to lose potential energy. So here's just some reminders that we can use some of what's going on. Potential energy is going to increase if the particle moves in the direction opposite to the force on it, which makes sense. And in order for that to happen, work will have to have been done by something external to your system. Potential energy is going to decrease if the particle moves in the same direction as the force on it. It's like a falling object. Now, that was a uniform electric field. Let's take a look at a non-uniform electric field. So in this case, we are going to have this positive Q charge. If we were to visualize the electric field, that electric field is emanating out equally in all directions, and it's getting weaker. So if we were to kind of visualize this field, it would look something like that. So we have an electric field that is changing directions depending on where I move around the particle. But as long as I stay in a single line, like if I go from here to here, the electric field's in the same direction, which is nice. But the magnitude is going to decrease. So if we put a test charge here at some radius, they're calling that RB. Let me clear the ink. Then what's going to happen is that if this Q0 is a positive charge, well, it's going to freely move from A to B because it's going to be repelled. If Q0 is a negative charge, then in order to get it to move from A to B, I'm going to have to do external work on it because the tendency of that particle is going to want to move towards Q, the positive Q source charge, rather than away from the positive Q source charge. So you could describe the force by Coulomb's law, whereas before we described the force with the parallel plate definition. So Coulomb's law says that our force is going to be 1 over 4 pi E naught Q times Q0 over R squared. So now if we actually move Q0 by whatever means, we don't know how it's being moved, just as it moves from A to B, the force isn't constant. So we're going to have to integrate. So what we have going on here is we have just our definition of work going from A to B. We're using dr now just because dr is a good variable for the radius here. But you could call this dy or dx if it was in one of those coordinate systems. So you plug in the force here, and then you integrate. So everything's going to be constant except for the, you're going to get the 1 over r squared. So when you take the integral of 1 over r squared, dr, then that's going to be the same as r to the negative 2. So when you increase the power, you're going to multiply by a negative, basically 1 over 1. And you're going to get a r to the negative 1. So that's what they're showing here. So therefore, since you get r to the negative 1, if I was to break this down, this just doesn't have a ton of steps on it. So we get basically negative 1 over r evaluated from RA to RB. So that's negative 1 over RB minus 1 over RA. So you notice that this is 1 over RA minus 1 over RB, but that's just the same thing as what you would get here. It's just been rearranged so that the negative has been distributed and the order's been changed. So, so here's that electric field radiate out in all directions. So once again, because the electric potential, the electric force is conservative, then that means that we're independent of path. So you can start at any location along the arc RA, and you can go to any location along the arc RB. And as long as you're going from a position of RA to a position of RB, you're going to get the same amount of work because the displacement in the R direction is still just going to be RB minus RA. So you would take that dot product FDR and still just look at the R direction. So comparing this once again, so looking at kind of like the parent functions that's being generated by this, this is going to be the potential energy, because we know that work is negative the change in potential energy. So we actually define U as 1 over 4 pi E naught Q over R. So this is really similar to the way the gravitational force and the gravitational potential energy relate, with that 1 over R squared for force and 1 over R for potential energy. But the difference is you have to include the signs of the charges in the calculation. So what that means is that if both of the charges are positive, then your potential energy is going to be positive. If both of the charges are negative, your potential energy is going to be positive, because negative times a negative is still positive. The only time you're going to get negative potential energy is if you have opposite signs. So your potential energy of your particle is going to be dependent on what the signs are. So that this is just a plain inverse relationship if the charges are the same kind, and it's actually going to be a negative. It's going to be the mirror of that if your charges are of opposite sign. And this is very, very important for you to remember. And in both cases, whether your charges are the same or different, they're going to approach, as R goes to infinity, our potential energy is going to approach 0. So the only way to get 0 potential energy would be to get the charges infinitely far apart. So then we have to consider systems of point charges. This is where it gets a little bit wonky. And you have to be very careful about the way that a problem is read. So if we have more than just 2 charges, then what we need to do is we need to think about the wording. So one of the ways these questions can be worded is you want to find the total potential energy of one of the charges with respect to the remaining charges. This is the way it is normally asked. So this is just like the questions you've seen before, where you might have like 3 charges here in a triangle, and you want to find what's the potential energy of this charge due to its interactions with these other 2 charges. That's the normal question. The more difficult question is this one. What is the total potential energy of the system? Now, the reason that's more difficult is because you have to consider how the system was created in order to determine the potential energy. So here's case 1. This is what we would do. So if you had a bunch of different charges, say these Q1, Q2, and Q3, we would say then bring a test charge into place and say, okay, what is the potential energy of that test charge due to those 3 other particles? So basically, in order to move Q0 into place, you'd have to do work related to each of those charges independently. So work would have to be done either positive or negative based on Q1, positive or negative based on Q2, positive, negative based on Q3. So you'd look at the interactions between each of those and essentially just use our point charge formula. So it would look something like this. So your potential energy of Q0 would just be the sum of 1 over 4 pi E naught times Q0, which is your test charge, times each of these. So the Qi could be Q1, so you do 1 over 4 pi E naught Q0, Q1 over R1, plus the next one, and the next one, and so forth. You just add them up. That's not tricky. But remember, the potential energy is a scalar value, but it can be positive or negative. But it is a scalar. Case 2, potential energy of a system of charges. So this is where we have to consider how the system was created. So what you would do is you would take, say, put a, the picture didn't pop up. Okay, so you basically put Q1 into place. That doesn't have, why is the picture not here? Okay, hold on. Let's draw a picture. Sorry, guys. So let's start this again. Start by putting a first charge in place. So Q1 is here. So basically, because I assume everything else is empty space, there's nothing else in my universe besides Q1 right now, then no work has to be done to do that. So Q1 goes into place. Now, in order to bring Q2 over here, basically I have to bring it from infinity and bring it to some position here. So I'm going to have to do work to bring that charge into place. Now that work is either going to be positive or negative depending on the signs of both. So some amount of work is done there. So that work being done, therefore, adds to the potential energy of the system. Now, if I bring a third charge into place, so say I want to put Q3 right here, then basically in order to move Q3 into place, I assume that I'm moving it from infinity and bringing it into this position. Well, it's going to be at some position from these other guys. So basically, I'd have to figure out the amount of work to bring it into a position here based on where it is relative to Q2. So that's a potential energy. Then I'd have to bring a potential energy to Q1 over into place. And I'd have to add that up. So that's like actually making this system. So basically you do that until all of your charges are in place. Your function would then be this. So you'd actually end up having to basically index each of the charges in this formula, because you'd first have to look at charge Q1, but there'd be no other charges, so you don't have to worry about that. So when I is 1, there is no J, so we don't have to worry. So then basically you want to look at the second charge, so then I becomes 2, and then J becomes 1. So then you would do that one, but then J can't be 2 in that case, so then you're done there. But then when Q becomes 3, then J can be either 1 or 2. So then therefore you'd have to add up for 1 and you'd have to add up for 2. So that's what that notation means. Now, if you just think about building the system one particle at a time, you don't have to remember the indexes I and J and so forth. But that's essentially how you would write that potential energy function. So here's an example. So you have 2 test charges brought separately to the vicinity of a positive charge Q. So in the first case, you have Q present there, and you're going to bring little q into point A. And then you're going to bring 2Q into a position relative to point B. And we want to compare the potential energy of Q and to that of 2Q so that they're independent. So pause, figure that one out. And then the next one I want you to figure out is this one. So now suppose charge 2Q has a mass of M and is released from rest. So this guy has a mass of M right there, is released from rest. What is the velocity VF as it approaches R equals infinity? So which one of those is? So pause that one and work it. When you're ready, hit play again. So looking at this first one, basically, since it's independent, we can just find potential energy Q over R just for the first case, for the particle at A. And then for 2Q, you're going to get also Q over R, but this time you have a 2Q and a 2R. So actually the potential energies are equal. All right, what about the second part? So in this case, if we're talking about speeds, we're talking about conservation of energy here. So you're going to want to set up a conservation of energy statement. So we can assume that at the instance, since it started at rest, that there's no kinetic energy. So you're just going to have potential energy. And that was the potential energy that we found in the previous part. And then at the end, we are going to assume that the charge has no potential energy because it's going to be infinitely far away. So there's going to be no potential energy. but you're going to have kinetic energy. So basically your kinetic energy and your potential energy from the start and end are going to be equal. And then sub in for your formulas and solve. And you're going to end up with Vf equals the square root of 1 over 2 pi e naught QQ over m times r. There you go.